All right, hope you guys had a good long weekend. So let's get started. Okay, so last time we were talking about polynomial regression. So let's see, so we're doing this. And we have a single scalar feature x, but what we can do is we can take it to different powers, all the way up to the dth power. And we can fit this model using the same techniques we learned in the last unit, because essentially we're just creating new features, and we can think of those new features as x sub j, even though they're, in this case, x to the power j. And you could, of course, you could do this with other nonlinear transformations, cosine, tangent, whatever you want. You can create all these extra features, and there's the temptation to do this is that by constructing these extra features, you can get much more sophisticated models. So in this case, if we plot the modeling function in the original feature x domain, then you can see we have a polynomial. But there's a new problem, is that if you create too many features, as we'll see soon, that this leads to a new problem, a problem called overfitting. And so we had some pictures. So when your model order is too small, when your model is too simple, that's called underfitting. And we have an example here where we generated the true data points using this cubic model, and we're fitting it with a linear model. And you can see it's not doing quite as good as the cubic model. On the other hand, we could try a 15th order polynomial, which is overkill. And what that's going to do for us is we're going to start to get all these wiggles. And basically what's happening is this model is trying to fit the noise in this particular data set that we created. And there's some other pictures down below. Like, it's possible in some cases that you could actually go through all your training samples perfectly, where you have no training error. But the issue with that is that the test points are not going to be corrupted by the same errors. And so maybe the test points are over here. And you can see that model is actually going to be doing worse than a model like this. So our objective in this unit is called model order selection. We're trying to figure out from the data alone, what is the correct model? We don't want something that's too simple, nor do we want something that's too complex that fits the noise. We want something just in the middle that fits the main trends without getting distracted by the noise. Yes?
That x represents single feature, right?
Yes, so in this case, in all these pictures here, we have a single scalar feature x. Yeah.
But single x is raised to the other powers.
Yes, exactly. For this polynomial model, we just raise x to many different powers, and we have a different linear coefficient on each one.
Yeah.
But we're doing this mainly for visualization purposes. You can also imagine if you have more than one scalar feature, you could take them to different powers individually. You could also multiply them together with different powers. You can create all sorts of new features. And so a lot of the themes here apply more generally. Okay, so we also proposed to do something simple, but was actually kind of naive, where we said, let's make a list of hypothesized model orders like d equals 1 through 14, and for each one, we'll fit the coefficient vector of length d plus 1 to the training data. We will compute the training, this is called the sample mean squared error. This is just like RSS, but divided by the number of samples. We compute this quantity on the training data, and we plot the value of that quantity. And you can see that as the hypothesized model order gets large, that training error gets smaller and smaller. So this is not going to be a useful technique for us, because it's always going to tell us to choose the largest model order, no matter which ones we hypothesize. So remember that in this particular experiment, the true model order actually happened to be 3. So this is what we're shooting for, and you can see it's possible to get much smaller training errors by overfitting the data than even is possible at the true model order. Okay, so now we're going to move on and propose a methodology which is the standard methodology to make sure that this situation, this overfitting situation, is prevented, and it's called cross-validation. The main idea is to evaluate the performance on test data that is independent, that's different from the training data. So we use the training data to get the beta coefficients, but then we use test data to choose the model order. Okay, different things. And we're going to talk about several ways to have test and training data independent. This is the simplest approach, is just partition the total data set you're given into two subsets, or sometimes we call them folds, two folds. One is a fold of the training samples, and let's say that there's n train of them. And then the remaining ones we use for the test samples. So in other words, we're just taking this big data set we're given, we're splitting it maybe in half, or maybe like 80%, 20%. We're splitting it somehow into two different folds. And now we do the same approach as before, where we have different hypotheses of the model order D. And we compute, we train or compute the least squares coefficients from the training data, but then we apply them to the test data in that we predict the test targets and we compute the test sample MSE. And if we plot this gives us the green curve. The blue is if you would have evaluated the performance on the training data. That's what we saw previously. This just gets better and better, smaller and smaller as the model order increases. But the green plot, you can see that these model orders in the middle give you better sample MSE than ones that are too small or ones that are too large. So this has the behavior we want, that somehow it's finding maybe not the perfect model order, but it's getting close. It's getting us in the right ballpark. Okay, so this is the approach, the simplest version of cross-validation. And the intuition behind what's happening is that, remember, overfitting is where you're modeling noise in the data set that you're training on. But the thing is, we're not fitting noise on the test data, and the test data is what we're using to determine our model order. So it's impossible to overfit, because we're not using, I guess you could say it's impossible to overfit to the noise in the test data, because when we train, we don't actually see that test data. The test data is only used for the model order selection. Okay, so this is the main idea behind cross-validation, or at least in its simplest form. So what questions do you have on this? Is it making sense? No questions? Okay. So can anyone see a sort of difficult trade-off that we have in this case, a difficult decision to make? Yes?
How much should we split the percentage for test data and training?
Exactly, because intuitively, we want as much training data as possible to get a good model, but at the same time, we want our testing to also be accurate, because if I have too few test samples, maybe I won't get a good indication of what's the right model order. So, ideally, I want both my test and training to be large, but I'm given a finite set of data, and I don't have that luxury. I'm forced to split it into two. So that's the issue with that approach. So there's a more sophisticated approach that we can use, which is called K-fold cross-validation.
So you said the issue is deciding how much to split the data.
Yes. So that's one question we have. For example, you might choose, this is probably the most common choice, is use 80% of your data for training, 20% for test. But the point is that if you could have more test samples, you would have more accurate test results. If you had more training samples, you would have more accurate coefficients. And so the fact that you can only use 80% for training, is not ideal. The fact that we can only use 20% for testing is not ideal. Okay, so in k-fold cross-validation, this is what we do. We take the data that we're given, which we're representing by this block here, and first step is we shuffle it. So I'll write shuffled training data set. So we just randomly sort the order of all the samples in our data set. Then we're gonna basically split this data into test and training k different ways. K is gonna be some number we choose. Typically, k is like 5 or 10 in practice. So in this picture, k is 10. So this would be k equals 10 here. And this is what we do. So in the first iteration, you could say, we split our training data set into k folds. So here we have k different folds. We're going to use one as the test fold, and we're going to use all the other ones as the training. So with the training folds, we compute our beta coefficient vector. We then apply that beta coefficient vector to the features in the test fold, and we try to predict the labels in the test fold, and we measure the error. We see how good is the sample MSE or the RSS, whatever you want to use. We see how good is that prediction error in that test fold. And then we repeat the process. The second time, we use this one as the test fold, and we use everything else for training. And once again, we fit our beta coefficient vector. We're going to get a different beta vector than the first time. We then use that beta vector to predict the test labels in this fold, and we compute the errors on those test labels here. And these numbers, E1 and E2, are going to be a little different, hopefully not too different, but they're probably going to be a bit different. And we repeat this k times until finally we use this one for our testing and all these for our training. And at the end of the day, we're going to get 10, or however many k is, k different k different versions of your test error. And then finally, we're going to average those over k. And that's going to be the final test error for this procedure. Okay, so one nice thing you can see is that we are using all the samples as test at some point. Whereas like in this previous situation here, some samples were only used for training, some samples only used for test. In this new procedure, all samples are used for training, all samples are used for test. We're just doing it in a more sophisticated way. The main issue with this approach is computational. It's expensive because we have to fit our model k times. And if fitting that model takes a long time, now we've just multiplied it by k. And so with some methods like neural networks, this is rarely done, because maybe with a neural network, it takes so long to train it once, you just don't have the budget to do this k times. But with a lot of classical machine learning methods, this is the standard procedure. If you can train your model quickly, this is going to be a really good thing to do. If you can afford it, basically. Okay, so that's the approach, that's k-fold cross-validation. What questions do you guys have on this? Yeah.
In this approach, why not choose 10%, 20% randomly? What's the difference between the performance? Instead of getting each time 10% specific marks, just each 12 times you run 10 iterations, each time get 10% of the samples randomly.
I think probably in practice there wouldn't be maybe a huge amount of difference, but this one is maybe there's something that's more deterministic and just easily done with it. You're guaranteed to use every sample equally. Either you're going to use it for training k-1 times, for test a single time, whereas in the random approach there might be some samples you miss, there might be some samples you use more often. So we will eventually talk about something a little similar to this in a later unit. But for now, this is just the standard approach. This is kind of what people do. I don't know if that answers your question, but yeah. Okay. Any other questions? Yeah.
Is it going to, like on the second iteration, is it going to pass down the coefficient, the weights from the first one?
No, everything is done independently. So in the first iteration, this training data is used to compute the weights. The weights are applied to test performance here. Then you forget about those weights. In the next iteration, you compute completely new weights from this new data, and then you test it on this. So you forget about the weights from the earlier iteration. Okay. Any other questions? Yes.
Is the training set divided like this, or do we also have a separate testing set?
So for now, I'll talk about that a little bit later, but like for right now, we don't have any other separate test. There are cases where you do for other reasons I'll talk about, but like for right now, we're given this full data set, and we are sort of dynamically creating test and training folds in different ways as we go through the iteration.
Avoiding overfitting there?
Sorry?
How are we avoiding overfitting there?
How are we avoiding overfitting? Because, for example, like we're training, with these folds, and then the test data is separate from the training data. So just like on the previous page, we're avoiding it in the same way. There's no way that I can fit to the noise in here because I haven't seen that data when I'm training my coefficients. Okay, question?
I might have missed it, but do you just pick the set of betas which minimizes the error? Like you just pick the set that has the lowest E for the final model that you need?
That's a great question. We didn't talk about that yet. So the question is, what are the final betas, right? Because we talked about essentially what we're doing is we're getting a different set of betas for every iteration. And we're doing that in order to try to compute this test mean squared error, which is essentially like one of these green points. So maybe I hypothesize a model order D equals 1, and I do k-fold cross-validation, and at the end I get that 1 point. But I feel good about that point in the sense that I know I'm not overfitting to it, and I know that I don't face the same trade-off between test and train that I did before. So I've avoided those issues. Computationally, it's now taking me k times as long, but I get that point. And now for the next D, I get this point. And I do this, for each one of these points, I do k-fold cross-validation. And then, the simplest approach is then look at which one of those green points has the best sample mean squared error. Let's say, okay, it's D equals 5. So let's say that here it's this one. So now I finally know my model order D equals 5. I know how many beta coefficients I'm going to have. And now that I know that, I go back and I use my full training sets. I use all the data for training because I've already done my model order selection. So that is how I get the final betas, using all the data.
So there's a question more on the samples. Typically, when you would want to do these training sets, you would want the samples to be, valid samples, so not have large outliers, et cetera.
Mm-hmm.
And I know that the outliers would increase the error rates when you do these trainings. But typically, would you discover if those samples are good or bad after you do this calculation, or would you find it before?
I would say we're not going to get too much into the data cleaning outlier stuff, but you probably want to do that as the very first step, is figure out what are outliers if possible, get rid of them, and then do your processing on what remains. Yeah. So, Okay, so
So what do you do with that D value?
the D value is the purpose of this whole unit is called model order selection. We are trying to figure out how complex of a model to use. In this case, what polynomial order do we want to use? D is the polynomial order. Okay. Okay, great. Any other questions? All right, so there's an extreme version of this k-fold cross-validation where k is the number of samples. What that means is that in each one of these iterations, there's only one sample in the test fold, and all the other samples are used for training. So that's, in some sense, the best you can do because you use essentially the maximum amount of training data every time you train. However, it's also the most computationally intense because you're going to have n iterations, and if n is your data set size, and that's huge, it's just a massive amount of work. But anyway, just to know what it is, it's called leave one out cross-validation. That's just like the extreme version of k-fold cross-validation. Okay, all right. So is that making sense, k-fold? Okay, so let's take a quick look at how this is implemented, or at least one way to implement it. And essentially, you do this with two different for loops. There's a for loop here, which is over the folds, and then there's a for loop here, an inner loop, which is over the model order. Okay, but let's go back to the beginning. So here we're saying, okay, k is going to be 5 in this example. And if you think about like the difficulties in programming this, the trickiest thing is really going to be figuring out which indices of your training data are in which fold, and just dealing with all those index sets. That's the trickiest thing if you really tried to do this just completely from scratch. And so what scikit-learn gives you is it gives you this thing, this k-fold object, which does that hard stuff for you. So here, notice that what you tell the k-fold object are how many splits do you want to use, and do you want to shuffle your data in advance? And you want to shuffle your data essentially almost in every application. There's not really too many applications where you don't want to shuffle your data, at least in this class. Let's say we always want to shuffle our data. And then that's where you tell it how many splits you're going to use, in this case 5. The other thing we're doing here is we're just setting up an empty, or we're setting up a vector of the different model orders we want to test. We're just going to go from, in this case, from 0 up till 9, and we'll use those later. And so this is how we do the outer loop. So I don't know if you guys are familiar with this style of for loop in Python, but it's kind of interesting. It's where you have for something, comma, something in enumerate. So this is how it works. This I split is your typical for loop variable, which starts at 0, goes like 0, 1, 2, 3, like that, over the for loop. And I think in this particular example, we're not even using that, but it's, it's some, oh no, here we are using it once. But it's something that, is probably there in every for loop. But the other stuff in this for loop is interesting. As you go through the loop, this enumerate is going to call this k-fold operator. In particular, it's going to call the splitting function. And here you're giving it your x data. And this is really, it's just using this to know how many samples do you have. And what it's going to do is it's going to give you, every time you go through this for loop, it's going to give you the index sets that correspond to that fold. And in particular, it's going to give you the training index sets. So it's going to give you a list of all those indices and a list of these indices. So let's go back down. So this quantity here, you have to unpack it into the training indices and the test indices. But once you have them, you can get the training data, the training feature data from your X data vector by just plugging in this list of indices. So this just sort of extracts those training indices. Now you have your training features. You do that with your targets, and now you have your training targets. You have your test features and test targets. Okay, so in the outer loop, these things are done once per outer loop. And then the inner loop goes through all the different model orders that we're testing. And D is just the variable for the model order at this iteration of that inner loop. And so here you can see we're doing our polynomial fitting. This is doing our least squares fitting, giving it our training data, features and labels, and the model order we're using. And this gives us our least squares beta coefficients. Then we use those beta coefficients and we do polyval, which makes our prediction from the test features to give us the test targets. And finally, we compare our predictions and the true test targets, and we look at the mean squared error, and we enter that as one entry in this array that we're building. So we're basically building this array or this matrix of values where this is another way to think about it here. So it's like this array of numbers where as you go down one dimension, you get the different iterations in k-fold. And as you go, sorry, that's this high split. And as you go the other direction, you see the different hypothesized model orders. So essentially the point of this code is to fill out that big array of data. Once that's filled out, you can get, you can average across your folds to get the sample mean squared error for that Dth, that model order D. And so here, notice we're using a bar. This is the sample mean. So we're just saying we're taking the sample mean of all of our different cross-validation samples at that D. And essentially, this number is what we plotted over here. That is these green points. We're just computing a vector of those. And then once we have that vector, we can just look through it and see which is the model order that gives us the smallest cross-validation mean squared error. Okay, so this is how this k-fold object helps us and makes the coding pretty straightforward. Okay, any questions?
For the first for loop, right? You said that is depicted in the training set image that you showed us.
The first for loop, yeah, the first for loop basically goes through those iterations.
Okay. And the second one, is that also depicted in that image or no?
It's not really depicted here. Now, essentially, we're saying once you have, let's say, this training data set and this test data set, what you do is for all the different model orders you're considering, you fit the parameters and you test those parameters.
Okay. And that would be like when you were giving the example of fuel efficiency and weight and stuff like that, right? Or do I have that confused?
That was in the last unit. We don't have that data set in this unit, but
So what would be an example of a model order?
we're fitting a polynomial. So a polynomial has different numbers of coefficients, right? And so here we're plotting the model order and we're plotting the mean squared error as a function of the model order. Okay, so all right, any questions? Okay, great. So so for the values we compute, they're not perfect. If you think about it, there's quite a bit of randomness to these different values and therefore to this value. So for example, if I shuffle this again in a different way than I shuffled it the first time, I would find that you're going to have different test samples, different training samples. All these numbers would change a little bit, right? Every time you do this, things are a bit different. Nothing you compute is perfect. They're all, you could say, sort of random approximations of some maybe true quantities. And maybe to even think, what do we mean by true quantity? Well, maybe if we could somehow do this an infinite number of times, maybe we could converge to where this number would stabilize, this average would stabilize, and that would be the true quantity. So if I just do this once, the numbers I get are not going to be perfect. And it's going to be important to understand how perfect or imperfect they are. especially when you look at pictures like this one here. Like these three numbers, the heights of the green, they appear to be very similar. Statistically, are they actually different, or are they more or less the same? Like, is there some sort of like statistical errors that essentially tell us like, there's really no difference between them? So that's what we're going to talk about next. And one of the nice things about K-fold is that we can look at how much change you see across these different values to get a sense of how stable or how trustable this average is. If you see that these are all very consistent, then you would feel good about their average, right? But if you see that these are wildly different and you're averaging just a few of them, intuitively you're like, okay, averaging has made things maybe a little bit better, but there's still a lot I should not trust in the number I get out. So that's what we're going to talk about next.
So my last question, sorry.
Yeah.
So for each iteration, we're graphing 8 different polynomials to fit the data. Is that correct?
Are you referring to this?
Yeah, and the code that we're looking at as well.
So the code is computing these points. Right? As
So
the,
8 points for each iteration.
no, each one of these points is an average of all the iterations. Okay, so this is what we're going to do to understand this. So this is what we're saying. This number we're computing, which is the average of our K sample MSEs. This is not perfect. There's some true mean squared error, and notice there's no sample. This is like something that's to do with the population. And we want to know, like, how close is this to the true one? How perfect is it? So this is probably something you guys have seen in many different forms before. Whenever you see a plot with error bars, that sort of means that this value that's computed here should be taken with some suspicion. This sort of gives you some sense of the maybe what the true value is. It's somewhere in that interval. So even though this is the number we got, there could be some error, and the size of the error bar tells us how much the error is. So the question is, how can we compute these error bars? So the main way, whenever you see an error bar, and it has to do with some sort of average statistic like this, the error bar is referring to what's called the standard error. And the standard error is defined like this. You take the standard deviation of your sample MSE quantities, and you divide by the number of terms in the average. So this sample standard deviation is given by this expression down here. So notice that if you get rid of the square root, it resembles the standard, the sample variance. And it's the same as the sample variance that we saw in the last unit, except now we're dividing by k minus 1 instead of 1 over k. And we'll talk more about this. This is known as the unbiased estimate. We'll talk more about that later in the unit. But this is helpful when k is small. When k is small and you use 1 over k, there's some sort of offset to the values you compute. They're not correct, and this is trying to remove that offset. Otherwise, you can see we have the mean and the individual elements, and we're just essentially looking at the average of the squared difference. Okay, so we plug this into here, and then we divide it by the square root of the number k samples that we're using. And this gives us the vertical height, the height of the error bar. So this would be like plus a standard standard error, and then minus a standard error. Okay. So one thing I want to emphasize is that this standard error stuff is much, much more general than what we're talking about here with sample, MSE, and K-fold. Like, for example, if you had data on salaries at graduation, you had 100 examples of a salary at graduation, and a natural thing to do would be to compute the mean salary at graduation, right? That would be computing this. But then you would wonder, okay, that's the mean salary, but how much should I trust that? Is that a rough number, or is that a very precise number? So you could then compute the standard error on it. You would look at the standard deviation of the numbers in your list, and you would divide by square root of 100. And that would give you a sense for how much you should trust the mean you computed. Okay, so this is a general concept. Here we're applying it to K-fold optimization or K-fold cross-validation, but you can use this for anything. So maybe this shows up on a homework or test, and it has nothing to do with cross-validation. It's just standard error, but applied to something else. Okay, so it's just a general idea. And like I said, whenever you see error bars in a graph, it's very likely that they are standard errors. That's what they are, usually. Okay, so when you look at this, we computed the standard errors here, and you can see that, I guess number one, this curve now is slightly different. These values where the line is are slightly different than the last time you've seen it. That's because I used a different shuffling. So it's always a little bit different. And but another thing you can notice here is that even though, I don't know, let's look at these. Even though this one seems to be a higher value than this, right? These error bars are telling you that you shouldn't really trust the very specific value here. It could really, the true number could be anywhere in this range. The true number could be anywhere in this range. So it says to be careful, don't really trust these more than you should. And this one you can see has a much bigger error bar. Okay, so what questions do you guys have on this? Anything? When we look at the code, we notice a few things. So this is a matrix. So when you take a mean of a matrix, you have to tell it, are you taking a mean over the rows or the columns? So in this case, we're taking a mean over the columns. Is that right? Should be, yes, mean over the columns. And in order to compute this quantity, this DDOF is what controls that, how much you subtract from K. So for example, if you wrote DDOF equals 0, you'd be subtracting 0 from K here. If you wrote DDOF equals 2, you'd be subtracting 2 from K here. Other than that, I think everything in the code just matches the expression exactly. And then we're using error bar to plot it. It just gives that nice plot with the error bars like this. Yes?
It's what? So it's DDOF is blank degrees of freedom. What's the first piece to it?
Oh, what does DDOF stand for?
Yes, it's
I don't remember. We'd have to check the documentation. It's not important. It's just remember it's DDOF means the number there. Okay.
You said axis 1 is what determines that it's over the columns?
The axis tells you whether you're averaging over rows or columns. So yeah, basically with a matrix, row would be 0, columns would be 1, like that. Okay. All right, so now let's put these ideas together. Now that we know how much we can trust the different numbers we've computed with cross-validation, we can use something called the one standard error rule. And the one standard error rule is based on a principle similar to what's called Occam's razor, which is if there's multiple explanations that are all equally good, choose the simplest one. You can think of D, the model order, or you could think of each of these models as different explanations for your data. As the model order gets bigger and there's more coefficients in your model, that's like giving you a more complicated explanation for the data. And this rule basically just says use the simplest model as long as they're all pretty equivalent. And by equivalent, you look at the so-called best model, which in this case, you essentially look through the model orders to find which model order has the smallest cross-validation. It turns out to be this one in this example. So we're going to call this one D-min. It's hard to tell from the blue curve because all these values look equal, but this one is just slightly lower. So if you were just saying what's the model order that minimizes cross-validation, it would be 7, but you can see, we know that the true one happens to be 3, right? And you can see 7 is really over-predicting. But then when you look closely and you look at all the standard errors, you can say, okay, but actually, even though this is the number I think it is, really it could be plausibly anything in that range, and same with this one. So that sort of means that these guys are all more or less saying the same thing. They're giving you the same errors, more or less, and so let's just choose the simplest one, which is this one. Okay, so how do we do this exactly? First step, this is just a turn the crank procedure, something good to memorize. So the first step is you find the best model, meaning the one that minimizes the quantity of interest. So in this case, sample mean squared error. Then you set the target as the top of the error bar there. So this is the top of the error bar at D-min. This is our target. That's that orange line. And then you say find the smallest d such that the value is less than or equal to the target. So when you go to the left, you find that, and now we're looking at the line, not the error bars. So this is clearly below the target level. This is 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 not. Okay, so the simplest one that is below the target level would be this one, and that would be what's called the one standard error estimate, DOSE. And here you can see DOSE managed to get the true model order. It doesn't always work perfectly, but usually does a pretty good job. And you can see it took us from 7 all the way down to 3. Okay. So that's another nice thing about k-fold cross-validation, is it allows you to get an estimate of the reliability of the different numbers that it computes. And then you can use it in something like this. All right. Any questions? Making sense? Okay. There will be some homework problems to play around with that. Okay, so and now finally we'll get back to a question that was answered or asked earlier today. Sometimes we see data that's partitioned 3 different ways instead of 2. Until now we've thought about training versus test data. Sometimes you actually have this third set. So let me try to clarify what is meant by these 3 different sets. So the training data is the data that is used to train the model parameters. So in this case, it would be the beta coefficients. The test data is data that's used for the design, but for some sort of higher level design thing we call the hyperparameters. And an example would be, in this case, the model order, D. So the model order is not directly one of our parameters beta, but it tells us how many betas we're going to use. So it's an example of a hyperparameter. Both of these things are used to design your model. This is for design. And now the validation data, if you want to use it correctly, you only use it once your design is complete. And the validation data is this fresh data that allows you to see how well your model is going to work on unseen data. So I'll write here, this is like post-design, after you're done designing. And one of the ways this shows up is when there's a machine learning contest, there's validation data that is held out by the contest organizers, is never shown to any participant until after the contest is over. Then all their models are evaluated on that validation data, on that unseen data, and finally judged on that data, not on the data they were given. And by withholding it from them, you prevent them from ever using it for design. Now the thing is, like, you might be tempted if you're doing a design, like in the final project of this class, you might be tempted, I give you a bunch of data, and you split it up into training and test, let's say. The more times, even though the test data is not directly used to design your beta coefficients, it is sort of indirectly used for your design, right? And it is possible if you keep doing, let's say, keep making new designs and testing them on this test data over and over and over again, you eventually will start to overfit to this test data because you've used it so many times in your design. And it could be that your model that comes out of that process, where you go back and forth between those, eventually performs quite poorly on unseen data. Because really, even though you didn't use the test data directly for the betas, you implicitly used it for the betas because you used it so many times, you eventually you found this special magical beta combination that worked great on that test data, you eventually overfitted it. So that's what the validation data is supposed to be, new data that is not corrupted by your design process. Is that making sense? How we would have these three? Yes.
Is the one standard error rule used to prevent that from going back and forth too many times?
No, the one standard error rule is just one of the techniques you could use for hyperparameter tuning. So it's not always used, it's sometimes used. Like if you didn't use it here, you would have chosen a model order of 7, which is much bigger than 3. As you can see, according to this test data, it doesn't perform like that much worse. It doesn't seem like it's overfitting that much, even though it is bigger than we need. At least according to this test data set, but maybe if we would apply it to a different one, maybe things would be a little different. Okay, any other questions on these three data sets? Okay, so, and now just a caution, is that there's no consistent terminology for test and validation. In other words, in a lot of different sources, those two terms are swapped. So some people, they think of validation as what you use for the hyperparameters and test data for the last step, and other people the other way. So there's just no consistency there. So just be aware that those two things are kind of interchangeable. Depends who you're talking to, what book you're reading. But in this course, we will try to be consistent. Test and training data are the things we use to design our model. And validation data is data that's held out that we only use to evaluate our model after it's done designing both the coefficients and everything else. Okay. All right. Great. So we covered a lot of important things today. Any questions on anything so far? Cross-validation, anything? Okay. So we're going to kind of sort of switch gears a little bit and then come back and combine everything in the end. And when switching gears, we're going to start to talk about more statistical things and probabilities. And the motivation for doing this is that we want to generalize the concepts we've learned until now. Until now, we've been focusing on polynomial regression, but we want to apply these same ideas more generally. And in terms of underfitting and overfitting, these are kind of very generic ideas that that manifest whenever you have data models that are either too simple or too complex. And what we'll see is we're going to focus on something called the statistical mean squared error. And you can contrast this with sample mean squared error is, I'll write here, similar, but, similar but different. So in the sense that, we'll talk about these in a moment. So in order to get into this, we're going to talk about random variables. We'll start talking about probability. And so this is another one of those things that's part of the prerequisites for the course. I understand that probably, most people don't love probability. I think the way that it's taught is often kind of dry, and you maybe don't really see as an engineer like why it's that important. So part of the role that class like machine learning plays in the curriculum is to try to give you an appreciation for why it's important, why you should care. Of course, we do have to get into a few details, and I don't have time to teach you a whole course on probability, so I'm just going to focus on these are the important things. This is the notation I'm using. There's really not too many things we need to know, to be honest, but I do want to go through it just to make sure that we have the same notation and sort of jog your memory. And I did write a document kind of like, I don't know if it's 10 pages or 5 pages. It's a short document written like textbook style that just goes through all the stuff in these few condensed slides here, but with more words, with examples. And so I really do recommend that if you want to kind of brush up on this stuff, take a look at that document. I try to put in there all the stuff that we need, no extra stuff. The advantage of that over a textbook is you go to a textbook, it's like hundreds of pages of stuff. A lot of it we don't really need. And I've just tried to put what's important in there. So that's something to note. You can just click on that green link. Anyway, let's start at the top. So we're talking about randomness now, and we're going to be talking about things called random variables. So a random variable, I think like an analogy is it's like a big bag of marbles. If I have a big bag of marbles and I reach in and pull one out, many things can happen, right? I could, and let's say each marble has a digit or a number printed on it. So every time I pull out a number from the bag, it could be a big number, it could be a small number. And it's really how big or small, or that all depends on the properties of the bag itself. So maybe I have one bag of marbles where they're all zeros or ones. But then maybe I have another bag of marbles where I can have, real numbers that are positive and negative and so on. So if we think about the random variable as the bag, the random variable tells us everything about what can happen, how often those things happen. So that's sort of just an analogy of what a random variable is. So in these kind of introductory pages here, the random variables are capital letters, and the non-random ones are small letters. So there's essentially two kinds of random variables where the math is a little bit different between them. So we'll have to talk about them differently. We have discrete random variables and continuous random variables. Also, sometimes we talk about the deterministic numbers generated by the random variable. We'll call those realizations. So like if I pull a number out of the bag, that's a realization, whereas the bag itself, that's the random variable. Okay, so let's talk first about discrete random variables. So if I have a discrete random variable, here I'm calling it capital A. The main thing is it takes on values from a countable set of numbers. So countable set means like numbers I can put in a list and count. I can't do that with real numbers. It's impossible to make a list of real numbers because there's always numbers in between the ones you try to list. It's impossible to enumerate them. But with integers, if I give you like 10 integers, that's just a list of 10 numbers. Even if I give you integers from negative infinity to infinity, that is a countable list. So these discrete random variables, they take on values from this countable set. And here the superscript tells us the possibilities. So in this case, there's k possible values that A can take on. And the way we describe that random variable is all about its probability mass function, which is just the list of probabilities. So this is a list of real numbers. The first one is the probability that A1 occurs. The second one, the probability that A2 occurs, and so on. And as probabilities, these numbers must be somewhere between 0 and 1, and they must sum up to 1. So, so those are the key ideas behind this probability mass function. Now, if we're talking about a continuous random variable, this takes on an uncountable number of values from the real line. And so here we have to describe it in a different way. One of the ways to describe it, which we won't actually use very much in this course, is called the cumulative distribution function. And it's a function that tells you what is the probability that the random variable A is less than or equal to a value A. So this is just like a function of that value A. The thing we'll use more often is actually the derivative of that, which is the probability density function. And another way to see the connection between them is you can write the CDF in terms of the integral of the PDF up to the value in the CDF. The key properties of this PDF are that it must be non-negative and it must integrate to 1. So it's similar in spirit to this PMF, except the PMF is like a list of numbers, whereas this PDF is just a continuum of probabilities. Okay, I think we're out of time for today, but we'll continue with our review of this stuff on Friday. See you guys then.